In this video tutorial, we will introduce the concept of VSEPR as it relates to bond theory. So, VSEPR is an acronym and it stands for valence shell electron pair repulsion. Now, this name does a pretty good job of explaining what the theory is all about. Essentially, valence shell electron pairs repel each other, and the shape that the molecule takes is the one that has the least amount of repulsion, the one where the electrons are least crowded together. So if we take a look at this example here, if these two electron clouds are placed too close together, because they're both negatively charged, they would be repelled to the opposite direction. And the same applies on this side. Push these two electron clouds too close together, and again the negative charges would repulse them in the opposite direction. And so VSEPR states that when you have two electron clouds positioned like this, the ideal shape is a linear shape with a 180-degree angle in order to minimize the repulsion so that the electrons have the most amount of space between them, so that they're not crowded. Same thing over here. If I have three electron clouds positioned like this would be the ideal shape with a 120-degree angle between electron clouds in order to give them the most amount of room, the most amount of space with the least amount of repulsion. Now, when I ask my students what is the best angle, the most amount of freedom you can have when you have four electron clouds put together, many will say, oh, it must be 90 degrees. But that's not true. The actual answer is 109.5. You have to stop thinking two-dimensionally and start thinking three-dimensionally. So when you look at a situation where there's two electron clouds, so one over here in the chemical bond and another chemical bond over here, so two electron clouds, we get a 180-degree angle, the most amount of freedom you can get. If I add another bond, now it's going to be, remember, a full circle is 360 degrees, so divided amongst three areas, 120 degrees in each area. And of course, this is a nice flat plane. But the moment I add a fourth one, it doesn't become 90 degrees. Now it looks like this. It's a three-dimensional shape, and the best angle with the most amount of freedom is 109.5, not 90 degrees. To help you visualize these three-dimensional shapes, I highly recommend that you go to PhET VSEPR simulation. This is from the University of Colorado. Just click on the first link and it gives you a pretty good simulation for how you can visualize the VSEPR shapes and geometries. So, as you add more electron clouds, you get a new, different shape in order to minimize the repulsive forces between electron clouds. So add one more electron cloud and of course another different shape. So, to recap, VSEPR allows us to predict molecular geometry, or the shape of the molecule, based upon the following principles. First, the central atom, the one in the center, is going to be the atom with the most bonding capacity. So carbon, for instance, has 4 electrons, each able to bond with a different atom, while hydrogen only has 1 electron, so it's only able to bond with one other atom. So given the choice between hydrogen versus carbon, carbon is most likely to be your central atom. And the central atom is the one that plays the largest role when it comes to determining what type of molecular shape the molecule will take. Due to electrostatic repulsion between electron clouds, atoms will organize themselves in such a manner so as to minimize these interactions so that they're not too crowded together. Now, these repulsive forces are dependent upon whether the electrons are in a bonding pair or if they're in a lone pair. So as I mentioned earlier, carbon has 4 valence electrons, and that allows carbon to form bonds with 4 separate hydrogen atoms. These electron pairs are called bonding pair electrons because they're involved with the chemical bond. Nitrogen, on the other hand, has 5 valence electrons. As such, it can only form bonds with 3 separate hydrogen atoms. These are called bonding pair electrons because they're involved in the chemical bond, but these ones are called lone pair electrons because they're not involved with the chemical bond. Now, the reason why we have to care if it's a lone pair electron or a bonding pair electron is because lone pair electrons take up more space than bonding pair electrons. Take a look at these bonding pair electrons. How many nuclei are holding them in place? Because remember, nuclei are positively charged, electrons are negatively charged, so they're attracted to each other. So take a look at this. We have 2 nuclei. Nucleus of the hydrogen atom, nucleus of the carbon atom, holding these electrons in place. It's like having 2 parents watching over a pair of kids. When you have 2 parents watching a pair of kids, they tend to stay in the general area where they're allowed to play. While lone pair electrons are only held in place by 1 positive nucleus. So it's like having a single parent trying to keep track of 2 kids. Well, that's going to be very difficult, so they take up a lot more space. They're allowed to roam a little further away from where they're originally allowed to play. So bonding pair electrons don't take up as much space, and so they don't repel as much. Whereas lone pair electrons take up a lot more space, and so they force the other electron clouds a little closer together. And so over here we had originally an angle of 109.5 degrees between this hydrogen atom to this hydrogen atom, but with a lone pair electron pushing these guys closer together, that angle has been reduced to 107 degrees instead. So when you have bonding pair electrons that don't take up too much space, you'll get an angle of about 109.5 degrees. But if you have a lone pair of electrons that take up a lot more space because they're allowed to roam further away from the nucleus, now that really forces these guys together, and now your angle has decreased to 107.3. And then of course this third example, when you have two lone pair electrons each taking a lot more space, then of course the repulsive forces are even larger, and that squeezes it even further to 104.5 degrees. As such, repulsive forces increase from bonding pair repulsion to bonding pair lone pair repulsion, and then the most amount of repulsion occurs between lone pair and lone pair. And so the repulsive forces of lone pair electrons will distort the electron geometry, so the bond angles will be slightly smaller than what VSEPR would normally predict. Alright, so in this example over here we have a trigonoplanar shape, 120 degrees, 120 degrees, 120 degrees. But if I got rid of this bonding pair of electrons and put in a lone pair of electrons, because these electrons take up so much more space, it forces these two guys closer together. So this would be less than 120 degrees, while this over here would be more than 120, and this would be more than 120. Now let's take a look at these three examples. This molecular shape, the geometry in which the atoms are arranged, is called tetrahedral, while this one's called trigonopyramidal, and this one is called bent. But if you look at the electron clouds and how they're oriented, they all look identical. They look like a tetrahedral shape, essentially. But when naming the shapes, we can only look at the arrangement of the atoms, not the electrons. So over here, it's a tetrahedral shape, but this one's called trigonopyramidal because it looks like a triangular pyramid with a lone pair at the top that forces these three at the bottom to come down a little bit more, so it looks like a triangular-based pyramid. While this one is a bent shape or angular shape because, well, it's bent at an angle. So although their electron patterns are identical in each situation, the arrangement of the atoms are not, and so the name of the structure is based on the arrangement of the atoms only. Now, to help us classify and name these structures, we're going to use something called the ax system, where A represents the central atom, X represents the number of ligands bonded to the central atom, so ligands are either atoms or groupings of atoms. And then E is the number of unbonded lone pair electrons. As we saw, lone pair electrons have an effect on the angle and how closely these atoms are going to be squeezed together. So methane over here has an ax formula of AX4, A, one central atom, X4, because there's 4 groupings of atoms surrounding the central atom. Trigonopyramidal, so ammonia over here, NH3, is going to be A, one central atom, X3 hydrogen atoms, groupings of atoms together, and then E because there's one lone pair electron floating here. And then finally water, H2O, has a bent geometry with one central atom, A, 2 ligands, so groupings of atoms, X2, and 2 lone pair electrons, one over here and one over here. Alright, so all you have to do is just write down the ax formula for the particular chemical, go back to your VSEPR geometry chart, which hopefully you'll have memorized at some point, and just look it up. So if I have AX4, then it's a tetrahedral shape. If it's AX4E1, sawhorse or seesaw shaped. AX4E2, square planar. Now, a lot of you are probably looking at this and freaking out. How am I going to memorize all this? It's not that bad. A lot of these names are repetitive. So for instance, linear appears over here, and over here, and over here. So linear appears 3 times already. And a lot of these names kind of make sense already. I mean, bent, that's not too bad. Trigonoplanar, well, it's a triangle on one single plane. This one's linear because it's just straight. T-shape because it makes the shape of a T. This one's a sawhorse or a seesaw, and it kind of has a seesaw shape. So this is a seesaw in a playground if you've ever seen one of them before. Well, this is where one person would sit, there's the other one, and this lone pair of electron forces these electrons down into this area, making a, well, seesaw shape. This one's called square pyramidal because it makes a pyramid shape, and it's a square base, so flat square base with a pyramidal shape. While this one is called square planar because it's a square all on one single plane. All right, so this ax formula here would be A, central atom, X4 because there's 4 ligands, and E2 because there's 2 of these lone pair regions. So AX4E2. All right, so a lot of these names are repetitive, and with the exception of a few names like tetrahedral or octahedral, most of these names actually do make sense. I mean, trigonal bipyramidal. It is a triangular base, and it's pyramidal because it makes a pyramid at the top, but it says bipyramidal, so there's two pyramids, one at the bottom, one at the top, trigonal bipyramidal. So the names and the shapes aren't too bad. Now when it comes to angles, that isn't as bad either. I mean, this one is 180 degrees because it's a straight line, not too bad, that's pretty straightforward. This one's 120, again, 360 degrees divided amongst three areas, so 120 each. If you put a lone pair here, it squeezes it down, so then all you have to just say is less than 120. Really, the only weird angle you have to worry about is the 109 over here, 109.5 degrees. When you put a lone pair over here, it's going to be less than 109 degrees. When you put two lone pairs, much, much less than 109. When you look at trigonal bipyramidal, we see a 120 degree angle between these guys on the same plane. So 120 degrees over here. But from the top of the pyramid to the base, it is a 90 degree angle, which we see over here, 90 degrees. So really, this VSEPR chart is not as bad as you imagine it to be. Just try to understand what those angles represent and how those angles came to be, rather than just blindly memorizing everything. Anyway, let's try an example. Using what we just learned, let's try and predict the VSEPR geometry for nitrogen trifluoride. So the first thing I'm going to do is first figure out how many electrons I'm dealing with. So nitrogen trifluoride. Fluorine is a halogen, so it's got 7 valence electrons, while nitrogen is in group 15, so it's got 5 valence electrons. Since there are 3 fluorines, 3 times 7 is 21 electrons contributed by the fluorines, and 1 nitrogen, so just 5 electrons contributed by the nitrogen. This gives us a total of 26 electrons for nitrogen trifluoride. Just make sure you always have an even number of electrons. If you ever have an odd number of electrons, you've done something wrong. Next, I'm going to determine which one of my atoms is going to be my central atom. So remember, the central atom must be the one with the most number of bonding sites available. Nitrogen can bond in 3 different areas, whereas fluorine can only bond in 1 area. Because remember, each orbital can only hold a maximum of 2 electrons, and so these ones can have openings available for another electron to get a maximum of 2, while this one already has too many that are maxed out and only 1 that's available to bond. As such, I'm going to use nitrogen as my central atom, and then fluorine will be my ligands. Now I know there has to be at least a single bond between the N and the F. Maybe it's a double bond, maybe it's a triple bond, I'm not entirely sure, but I know there's definitely at least a single bond between them to connect them. Since these are bonding pairs of electrons, each one represents 2 electrons, I've drawn 2, 4, 6 electrons so far. I need to draw 20 more electrons. What I'm going to do now is give priority to the ligands, make sure they follow the octet rule first. And so, if I need to draw 20 more, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now let's recap how many electrons I've drawn so far. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons, but I need to draw 26 electrons. Since there's no more room available on the fluorines, I must give them to the nitrogen as lone pairs. Based on my Lewis drawing, nitrogen trifluoride has an AX3E AX formula. All right, so 1 central atom, 3 ligands, the fluorines, and 1 lone pair electron. Looking at my VSEPR chart, I see that AX3E is trigonal pyramidal, so it's going to look like this. Now, here's how we're going to draw this in 3 dimensions on a piece of paper. First, we're going to write down our central atom, which is nitrogen. So nitrogen will be in the center. Next, we're going to have a fluorine attached to it, but it's popping out of the page, as you can see. So if you look over here, this fluorine is popping out of the page. So to show it popping out of the page, first I draw the fluorine, and I'm going to draw a little line like this, a solid line, and that is to show that this is coming out of the page. If something's lying on the plane of the page, so lying on the page itself, just draw a regular line, fluorine. Now if something's going into the page, so notice how this fluorine over here is going into the page itself, we draw hatchet lines. Now to draw a hatchet line, I recommend that you start from largest to smallest. It just seems to be the easiest way to do it. So largest to smallest. And there's my fluorine. The reason why I recommend this is because too often students, if they draw from smallest to biggest, they'll do this. Let me see if I can do this over here. And just kind of disproportionate. Makes it look ugly, kind of messy. But I find that if you draw from largest to smallest, it keeps you in position so you're not taking up too much space. Anyway, next we're going to draw the lone pair electron at the top. So I'm going to put it at the top over here. Lone pair. And there you have it, my trigonal pyramidal, because it's a triangular based pyramid. Alright, so triangular base, and it's a pyramidal shape. Solid hatchet line means it's popping out of the page, whereas a hatchet line is going to show that it's going into the page. So there's my hatchet line going into the page, and then if it's just a regular line, that just shows that it's on the page itself. So on the page itself. And that's how you draw a three-dimensional diagram. All right, now take a look at this, the electron geometry. So if I looked only at the electrons, there'd be an electron here, 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 and here. The electron geometry is tetrahedral in shape. But if I look at just the molecule geometry, so only count just the atoms, the position of the atoms, then it makes a trigonal pyramidal shape. All right, trigonal pyramidal. Now you'll notice because of the lone pair electrons that force the electrons closer together, it's going to be less than 109.5 degrees. And if I had another lone pair there, it would be much, much less than 109 degrees. And the shape would be a bent shape because we're only looking at the atoms and their configuration where they're located. All right, so let's recap. The first step, draw the Lewis structure, including the lone pair electrons. So for that, you're going to need to recalculate how many electrons you're going to be dealing with. All right, so make sure you calculate exactly how many electrons you're going to be dealing with. Whichever atom has the most number of bonding sites will be your central atom. And then at that point, make sure that you have at least a single bond in between atoms, because it might be double, might be triple, but you know it's definitely at least a single bond. Then start counting out the number of electrons by giving the ligands priority, so make sure they follow the Octet Rule. Any extra electrons, give it to the central atom. We can then write out the AX formula. A is the central atom, X are how many ligands there are, 3. E is the lone pairs, there's only one lone pair. We can then match it up with the VSEPR chart, or if you do, have it memorized. And then from there, predict the bond angles, just keeping in mind that lone pair electrons will make those angles slightly smaller than what VSEPR would normally predict. Now let's try relating this back to our lesson from last day regarding hybridization. All right. So over here, what type of hybridization is going to be used by the nitrogen atom in the center? That's a common question you might encounter on a test. So if you recall, the nitrogen's electron configuration is 2s2. So this is period number 2. Oops, period number 2. 2s1, 2s2. So 2s2. Over here are the p orbitals. So then it's 2p1, 2p2, 2p3, 2p3. All right. So in the valence shell, nitrogen has 5 valence electrons. Okay, 1, 2, 3, 4, 5. Remember, we will use Hund's rule, stating that we have to fill up every suborbital first before we start doubling up. And of course, Pauli exclusion says maximum of 2 electrons, each with an opposite spin per suborbital. Now, how do we determine what type of hybridization? Is it going to be sp, sp2, sp3 hybridization? How do we know? Take a look at the nitrogen and find how many areas, how many regions around the nitrogen do you see electrons hanging around? So how many regions of electron density do you see around the nitrogen? I see 1 electron density over here, another set of electrons hanging around here, another set of electrons hanging around here, and a 4th set of electrons hanging around here. So altogether there's 4 electron areas. So because there's 4 regions of electron density, I need 4 hybrid orbitals. If I want 4 hybrid orbitals, I need to hybridize 4 orbitals. And that gets me sp3 hybridization. So on a test, I would say the nitrogen uses sp3 hybridization. Now let's confirm to see if this makes sense. So again, nitrogen has 5 electrons, and if we've hybridized them with sp3, we get, 1, 2, 3, 4, and now we have to double up, 5. Take a look at that. So now we have this one over here to represent the lone pair of electrons at the top of the nitrogen. So that's why there's a lone pair over there. And then each of these 3 can now form bonds with the fluorine. So fluorine can bond over here, here, and here to give you that full octet structure. So you'll see that hybridization is used to explain the layout and the configuration of electrons in this particular molecule, and it all seems to match up. All right, so at this point, what I'd like you to do is try out this worksheet over here. So with all these chemical formulas, I want you to try and draw their Lewis structures, identify their Axe formula, and then based on their Axe formula, identify what VSEPR geometry they're going to take. You can ignore what dipole represents. We'll talk about that one later on. And you know what? Maybe add in the type of hybridization around the central atom as well. So that's one additional thing I'd like you to play around with. The answers for all these other things over here are on the back, so you can double check. Don't be confused about this one over here. Notice how the ligands have lone pair electrons, but over here the ligands do not have lone pair electrons shown. That's just me being lazy, and I just dragged and dropped the first image I could find on Google. So whether you have them there or not doesn't really make a difference. Typically, you do have to show lone pair electrons around the central atom because they do make a difference, but lone pairs around the ligands, it's optional. I usually leave them out because it gets a little messy if you try to keep them together. So I personally prefer a nice clean look where there are no ligand or electrons shown, or lone pair electrons, I'm sorry, shown along the ligands. All right. So give this a try. The only ones you might have difficulties with are probably SEF6 and also SO2. You leave those ones out for now. We'll wait until later in the video to address those two. All right, so pause the video and then we'll go over the answers together once you are ready. All right, let's take a look at the first one, CCl4. So the first thing I'm going to do is count how many electrons I'm dealing with. All right, so carbon has 4 electrons, chlorine has 7, but because there's 4 of these chlorines, that's 28 electrons. 28 plus 4 equals 32 electrons. So remember, you should always have an even number of electrons. Since carbon has the most number of bonding sites, I'm going to make that my central atom. Chlorine, I'll write them out around it. I know that each of these chlorines must be connected to carbon with at least a single bond. Might be a double, might be a triple, but definitely at least a single bond. So I'm going to put that in. And now I'm going to make sure the ligands get the octet rule first. At least they fulfill the octet rule first. So I've drawn 2, 4, 6, 8. This one's going to be 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. And there we have it, 32 electrons. Everything's accounted for. 8 electrons for each of these chlorines. The octet rule seems to be good to go for all these atoms. Now, regarding its Axe formula, it's going to be an A for one central atom, X4 because there's 4 chlorines, and there are no lone pair electrons around the carbon, so just AX4. If we look at our chart, we can see that AX4 is going to be a tetrahedral shape. So I'm going to write out tetrahedral, and let's draw its three-dimensional structure. So we have 1 bond popping out of the page, 1 bond going into the page, and 2 that are going to be on the page itself. So 1 bond popping out of the page with a solid line, and then 1 going into the page with a hatchet line, and the other 2 are going to be on the page itself with a regular line. And there's my three-dimensional drawing. Now let's see what type of hybridization is occurring around the central atom, carbon. So we're going to count how many regions of electron density we see. So we see electrons here, 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 and here. So that's 4 regions of electron density, meaning I need 4 hybrid orbitals. So if I need 4 hybrid orbitals, I need to hybridize 4 orbitals. So an S and a P3 hybridization, and carbon has 4 electrons. So 1, 2, 3, 4, and that matches up because now each chlorine can now latch on here, 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 and here in order to form the octet structure and fill in all the empty orbital spaces. All right, so we're going to say it's sp3 hybridization. Let's take a look at the next one, Ni3. 3 times 7 electrons each, 21 electrons from the iodine, 5 electrons from the nitrogen, 26 electrons in total. Nitrogen will be my central atom, and iodines will be evenly distributed amongst them over here. I know it's at least a single bond. And then what I'm going to do, 2, 4, 6, I need to draw 20 more electrons, so give the iodines priority. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and I need to draw 2 more electrons, so I'm going to give them to the nitrogen as a lone pair. Thus, my Axe formula is going to be A for the nitrogen, X3 for the 3 iodines, and an E for the 1 lone pair electron around the nitrogen. Looking back at my chart, AX3E is trigonal pyramidal, So we have trigonal pyramidal. Let's try drawing the three-dimensional structure for this. So again, one popping out of the page, one going into the page, the other two are going to be on the page. So one going out of the page, one going into the page, one on the page itself, and then the lone pair also on the page itself. Now, what type of hybridization do we have around the central atom? So let's count how many regions of electron density. 1 region, 2 regions, 3 and 4 regions. So again, I'm going to need to use sp3 hybridization to get 4 hybrid orbitals. All right, so hybridize these 4 to get 4. And nitrogen, of course, has 5 electrons. So let's start filling it out. 1, 2, 3, 4. And now I'm forced to double up because I have no choice. 5. And there is my lone pair electron. And then, of course, these ones over here are now bonded with the iodines. So iodine can latch on over here, here, and here. So my hybridization does explain my diagram, or rather matches up with it. So we're going to say it's sp3 hybridized. All right, so this kind of gets repetitive. Let's try a different one that is going to be interesting, like ClNO. So 6 electrons on the oxygen, 5 from nitrogen, 7 from chlorine rather. And then we're going to get a total of 18 electrons we need to account for. I'm going to choose nitrogen to be my central atom because it has 3 areas where it can bond. Chlorine can only bond in 1 area, and oxygen can bond in 2 areas. So nitrogen has the most bond sites. Again, I know that over here there must be at least a single bond between them. I've drawn 4 electrons so far. I need to have 18 in total, so make sure these ligands get priority. Make sure they follow the octet rule first. So 2, 4, 6, 8, 10, 12, 14, 16, and there's 2 extra electrons left, so I'm going to put them over here. Oops. Now if you look at this, chlorine has 2, 4, 6, 8 electrons, so that's the octet rule. Good, stable. Oxygen has 8 electrons as well, 2, 4, 6, 8. That's also stable. But nitrogen only has 2, 4, 6, so that's not good. Anytime the central atom seems to have less than 8 electrons, that usually indicates that a multiple bond must be present. So what I'm going to do is I'm going to take the double bond, or the 2 electrons from here, and bring them down over here. So these 2 electrons, bring them down here. And now we see that there's a double bond between the nitrogen and the oxygen. Let's double check now. Chlorine still has 8 electrons. That's good. Now nitrogen has 8 electrons, 2, 4, 6, and 8. And oxygen remains with 8 electrons, 2, 4, 6, and 8. Now some of my students usually ask, why can't I bring these 2 electrons down here? Why can't I have the double bond forming on this end? Take a look at chlorine. Chlorine only has 1 site to bond with, so it can only make 1 bond. So typically chlorine does not form double bonds, whereas oxygen has 2 sites where it can latch on, and so oxygen is the more likely candidate to have a double bond form with it. Alright, so let's look at the Axe formula for this. A for the central atom, X for the 2 ligands, which are oxygen and chlorine, and there's 1 lone pair, so we're going to write down an E over here. Looking at our chart, AX2E is a bent or angular shape. Nobody's popping out of the page, everyone's going to be on the plane of the page itself. So there's my bent shape, my lone pair electrons, and then these guys are bent down slightly because the lone pair electrons forces these atoms closer together. Now let's take a look at what type of hybridization is going to be used over here. So again, let's check to see how many regions of electron density do we see around the nitrogen. We see 1 region of electrons, 2 regions of electrons, and 3 regions of electrons. Now VSEPR doesn't care if it's single or double bonds. As long as they're hanging in the same area, just consider it to be 1. All right, so 1, 2, 3 regions of electron density. So that means I need to have 3 hybrid orbitals. So in order to get 3 hybrid orbitals, I got to hybridize 3 orbitals. So hybridizing 3 orbitals, S and 2 of these P's gives you an sp2 hybridization, but one of the p orbitals was left unhybridized. Now nitrogen has 5 electrons to fill, so we're going to go 1, 2, 3, 4. Now I'm forced to double up, 5, and there we have it. There's my lone pair of electrons. I can form a bond here with chlorine. And a double bond is comprised of a sigma. So one of them is going to be a sigma here from the oxygen, so sigma. And also a pi. So remember, pi bonds are created when you have a p orbital that's going side to side. And so this is going to be one of my pi's over here. All right, so one of the hybrid orbitals will form a head-to-head bond with one of the oxygens. We call this a sigma bond. And then the empty p orbital for the nitrogen will bond to the p orbital of the oxygen. And when they're side to side, we're going to form a pi bond over here. So we say the nitrogen has an sp2 hybridization, and that of course does a pretty good job of matching up with our diagram, explaining away the double bond as well as the single bonds and the lone pair electrons. Let's do the same for H2S, 6 electrons from the sulfur, 1 electron each from the hydrogen, gives you a total of 8 electrons. Sulfur will be my central atom. I know there's at least a single bond between them. Hydrogens don't form doubles or triples, but anyway, 2, 4, 6, and 8 for the remaining electrons. They're going to be lone pairs. And now we've got an octet structure of the sulfur and a duet structure for the hydrogen because it can't have 8 electrons in the first shell. So everybody's pretty stable over here. This gives me an AX formula of AX2E2 because of the 2 ligands, the hydrogens, and the 2 lone pairs. AX2E2 is another way of getting a bent or angular shape. Again, the atoms are going to be on the same plane, but the lone pair electrons, one will pop out of the page and one will go into the page. So there we go, the 2 hydrogens on the page and the 2 lone pairs, one going out, one going in. This angle over here is normally going to be 109.5 degrees, but because there is 2 lone pairs pushing it down, the angle is going to be much less than 109 degrees. Up here, it's normally 120, 120, 120 degrees, but because of the lone pair, we would say it is just less than 120 degrees. What else did we miss? Because I forgot these ones over here. Normally, again, this would be 109.5, but because of the lone pair, we're going to say less than 109.5 degrees. And then up here, no lone pairs around the CCl4, so it's just a regular 109.5 degrees. Alrighty. Okay, so going back to this one, we need to identify what type of hybridization is occurring over here. So I see that there are 1, 2, 3, 4 regions of electron density. So that means I'm going to need to hybridize 4 orbitals. Alright, so 1, 2, 3, 4. So it's going to be sp3 hybridized. Sulfur has 6 valence electrons. So we're going to fill it in. 1, 2, 3, 4, 5, and 6. And oh, look at that. Those are my 2 lone pair electrons, which leaves me room to bond onto my hydrogens. So again, sp3 hybridization matches up with my VSEPR diagram. Everything's good to go here. sp3 hybridization. Now ammonium has 1 electron for each hydrogen times 4 equals to 4 electrons. 4 electrons plus the 5 electrons from nitrogen gives you 9. But oh wait, we're supposed to have an even number, not odd. Take a look at the plus. By having a positive charge here, you're saying you have 1 less electron. Alright, so 1 less electron than you normally would have. So 9 minus 1 equals 8 electrons. And there we have it, a nice even number. So here are the single bonds that we have. 2, 4, 6, 8. There's my 8 electrons. No need for the hydrogens to have an octet structure because they only have room for that duet. The first shell only holds 2 electrons. And nitrogen, of course, has 8 electrons around it, so that's all stable and great as well. So the AX formula for this would be AX4. So we're going to write down AX4, and that would be tetrahedral. Tetrahedral. All right, let's draw the 3-dimensional structure. Nitrogen, hydrogen, 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 hydrogen. So 1 popping out of the page, 1 going into the page, the other 2 are on the page. So popping out of the page, popping into the page, on the page, and there is my 3-dimensional drawing. Let me just fill this in over here. So again, it's going to be sp3 hybridization because we have 4 regions of electron density around the nitrogen. That will allow us to have 4 hybrid orbitals. Nitrogen has 5 electrons, so 1, 2, 3, 4, 5. Oh, but there is no lone pair here that I see, but remember, the positive ion charge means there's 1 less electron. So I'm going to go back here and delete that extra electron, and that allows me to have the 4 regions where I can bond my hydrogens. So each of these hydrogens will fill in here, 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 and here. So again, hybridization does a pretty good job of matching up with my diagram. Alright, so that's sp3 hybridized. Let's go try HCN over here. So 5 electrons from the nitrogen, 4 from the carbon, 1 from the hydrogen, adds up to 10 electrons in total. Nice even number. I know there's at least a single bond between them. I got to make sure that everyone follows the octet rule. Hydrogen, of course, only follows the duet rule. So that's 2, 4, 6, 8, 10 electrons that I've drawn in total. But now carbon is missing 4 electrons. It needs to have 8 in total, but it only has 2, 4. So that indicates I need to have multiple bonds. So I'm going to bring this guy down over here. All right, so these two, and now we made a double bond. Nitrogen still has 8, 2, 4, 6, 8, but carbon now has 6, 1, 2, 4, 6, but it needs to have 8, so that indicates to me it's probably going to be a triple bond. So I'm going to bring these guys down here, and let's see if that solves our problem. So hydrogen's happy, 2 electrons in the shell. Carbon needs to have 8, 2, 4, 6, 8, that's good. Nitrogen needs to have 8, 2, 4, 6, 8, that's also great. So there it is, HCN. Now let's take a look at the AX formula for this. So the AX formula is going to be A for the 1 carbon, X2 for the hydrogen and the nitrogen, and there are no lone pairs, so we're just going to leave it as AX2. AX2 is a linear shape with everyone on the plane of the paper, so nothing's popping in or out of the paper. So we'll leave that as linear, and that's pretty much our 3-dimensional shape because it is just 2 dimensions. Now, some students ask, how do you draw a double bond or triple bond popping out of the page or popping into the page? The answer is don't. Don't draw the double bond or triple bond popping out of the page. Make the other single bonds pop in and out instead. So for instance, over here, let's pretend this was a double bond. Obviously, that's not possible, but let's pretend this was a double bond. How would I draw this diagram in 3 dimensions? I would put the double bond on the plane of the paper itself and make the other hydrogens pop out of the page and go into the page, if that makes sense. Alrighty, so where possible, keep the double bond, triple bond on the page itself, make the single bonds pop out or in, and that way it simplifies your drawings a lot more. Alright, let's see what type of hybridization is being used. So we see 1, 2, 2 regions of electron density. So that means I only need 2 orbitals to hybridize, so I'm going to use sp hybridization. Carbon has 4 electrons, so 1, 2, 3, 4. And let's take a look and see if it explains things, or matches up anyway. So one of the SPs will be used to bond with the hydrogen. If you recall, a triple bond is made up of 1 sigma and then 2 pi's. Pi bonds, of course, are made up of p orbitals that are side to side, so this is where the 2 p orbitals are going to be. So one of the p orbitals is for this pi, and the other p orbital is for this pi. And then this last sigma bond over here, or rather single bond, is going to be used for the sigma. Alright, so this helps to explain our triple bond. Triple bonds are made up of 1 sigma, so 1 sigma, and 2 pi's, 2 pi's. So we have an sp hybridization. Alright, so before we go ahead and talk about SO2 and SEF6, the 2 examples I asked you to hold off on, let's introduce the concepts of expanded octet structures and incomplete octet structures. So, if you recall, Lewis structures can be used to show the electron configuration and bonding of atoms in molecules. So if you look at the Lewis structure for magnesium, nitrogen, and sulfur, we can see how many valence electrons are in each. If we look at the energy diagram, we can see, oh look, 2 valence electrons. Well, there's the 2 valence electrons in the electron energy diagram. All right. Same thing with nitrogen. Nitrogen has 5 valence electrons. Well, here's the second shell, 1, 2, 3, 4, 5 electrons. Sulfur, 6 valence electrons. If you look at the electron configuration, 2, 4, and 6. So by drawing these Lewis structures, it helps us to distinguish between lone pairs and bonding pair electrons. So it tells us which ones are easily more likely to bond with another atom. So, many stable molecules and polyatomic ions contain covalently bonded atoms having a noble gas electron configuration. If you recall, noble gases, that family of elements, are extremely stable. When we look at their valence electrons, they all seem to have 8 valence electrons. And so we came up with this octet rule that states that 8 valence electrons seems to provide physical and chemical stability. So let's try and draw the Lewis diagram for the nitrate ion. Nitrogen has 5 valence electrons, oxygen has 6, but there's 3 of them, so that's 18. And this 1 minus charge means there's an extra electron that wouldn't normally be there. So altogether, we have 24 valence electrons we need to account for. Since nitrogen has the most number of bond sites, I'm going to keep it as my central atom while arranging the oxygens around it. I know that there's going to be at least a single bond between the nitrogens and the oxygens, maybe doubles, maybe triples, but at least a single. I need to now account for the 24 electrons. So if I've drawn 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Make sure the outer ligands get priority in fulfilling the octet rule before you look at the central atom. So here we have the oxygens all fulfilling the octet rule. They're nice and stable, but the nitrogen is not. It only has 2, 4, 6 electrons around the nitrogen. So anytime you have a situation when there are fewer than 8 electrons on the central atom, this usually suggests a multiple bond is going to be present. So what we're going to do is we're going to take the electron from the oxygen and bring it down to make a double bond. Now that we've formed a double bond, the nitrogen has 8 electrons, 2, 4, 6, and 8. And each of these oxygens also have 8 electrons, and so we fulfilled the octet rule for all the atoms. Now don't forget to put square brackets around this because it is an ion, and to show the overall charge for this ion as well. Now a common question is, what makes this oxygen so special? Why should we form the double bond here? Why don't we form it here or here? The answer is, there's nothing special about this oxygen. The double bond could have been formed here. So anytime there's multiple locations where the double bond could have been formed and there's no reason for choosing one atom over another, that usually indicates that a resonance structure is present. So a proper diagram for nitrate ion should include all 3 resonance structures, and the real version is basically a hybrid of all 3, where the double bond isn't located in any one location. Instead, there is no double bond and there's no single bond, but it's going to be something in between, a 1 1/3 bond. Alright, so not quite a double bond, not quite a single bond, something in between. So how do I get that number? Again, 4 bonds, 1, 2, 3, 4, divided amongst 3 regions, 3 atoms where it's going to be shared. So 4 over 3, 1 1/3 bond. So as I said in a previous lesson, some textbooks will show it this way to show that it's not quite a solid single bond, and it's not quite a double bond because this is a dotted line, but it's somewhere in between. But on a test, I want you to draw this method over here because this shows me exactly it's a 4 over 3 bond, whereas this one just shows me it's anywhere between 1 and 2. It doesn't specifically or explicitly say what type of bond it is. Alright, so delocalized electrons, those that no longer stay in position, are responsible for this resonance structure. Alright, so what I would like you to do at this point is, for these 2 examples, SCl2 and CCl2O, I would like you to draw their Lewis structures, come up with their Axe formula, and from that determine what the VSEPR geometry is for each of these molecules. Then draw me the 3-dimensional diagram and tell me what type of hybridization is being used around the central atom of each of these molecules. So press pause. When you're ready, press play, and we'll go over the answer together. Okay, so with SCl2, chlorine has 7 electrons times 2 of them, so 14 electrons. Sulfur has 6, that comes up to 20 electrons. Again, make sure there's always an even number. Sulfur has the most number of bonding sites, so I'm going to put it in the center. Chlorine will be the ligands. Now, in between the sulfur and the chlorine, I know there's at least a single bond, so it's 2 and 4 electrons. Now, make sure the octet rule fulfilled around the ligands, they get priority first. So that's 2, 4, 6, 8, 10, 12, 14, 16. Now that I've got 16 electrons, I need to draw 4 more. So the extra ones must go around the central atom. So now I've got 20 electrons in total. If I look at this, the chemical formula, or the Axe formula rather, is A for the sulfur, X2 for the 2 chlorines, and then E2 because there are 2 lone pairs. Looking at my chart, AX2E2 is a bent shape. And there you have it. So my chlorine's going to be on the plane of the paper. 1 lone pair electron will be popping out of the page. The other lone pair electron will be popping into the page. Because there are 2 lone pair electrons, the angle between the chlorines rather, is going to be much less than 109.5 degrees. Now let's take a look at what type of hybridization is used around the sulfur. So we see 1, 2, 3, 4 regions where electrons can exist. So we're going to need 4 hybrid orbitals. So that means we're going to use sp3 hybridization to create 4 hybrids. Sulfur has 6 valence electrons, so 1, 2, 3, 4, 5, and 6. And these electrons over here are represented by the lone pairs, while these 2 bonds are available for the chlorines that are going to attach here and here. Alright, so hybridization does a pretty good job of explaining, or at least matching up with what we've drawn over here, sp3 hybridization around the sulfur. With CCl2O, we have 24 electrons in total. Again, nice even number. I know that carbon is going to have the most number of bond sites, so I'm going to stick it in the middle as my central atom. And then I'm going to make it single bonds connecting all of them, minimum. There might be double bonds and triple bonds, but definitely single bonds. And now I'm going to give the outer ligands priority with the octet rule. So 2, 4, 6 electrons, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. Since the carbon doesn't have enough electrons, it's got to fulfill the octet rule. It only has 6 electrons when it should have 8. That indicates to me the presence of a double bond or a triple bond. But where should the double or triple bond come from, the oxygen or the chlorines? Again, oxygen has 6 valence electrons, so it has room to attach to 2 locations, while chlorine only has, chlorine has 7 valence electrons, but only has 1 location where it can attach to another atom. So which of these two is more likely to form a double bond? It's the oxygen. So I'm going to bring these 2 electrons down here and form a double bond. The X formula for this chemical compound is A for the central atom C, X because there's 3 of the ligands, oxygen and the 2 chlorines, X3, and no lone pair, so it's just AX3. Looking at my sheet, AX3 is a trigonal planar shape with a 120-degree angle between each of these atoms. Because all 3 bonds lie in the same plane, hence the name planar, there's no need for you to draw the bonds popping out of the page or into the page. Looking at the central atom, we see there are 1, 2, 3 regions where electrons are going to hang around. Again, we don't care if it's double bond or single bond. VSEPR does not differentiate. 3 regions of electron density, so we need 3 hybrid orbitals. If we need 3 hybrid orbitals, we need to hybridize 3 orbits. So I'm going to hybridize these 3. Now another common question students will ask is, why not hybridize these 3 instead? Well, when you hybridize something, you are mixing different things together. So my child is a hybrid of Chinese and Caucasian. You can't mix 2 Chinese people and say it's a hybrid. Chinese plus Chinese equals Chinese. But Chinese plus Caucasian, now that's a hybrid. Well, same thing. Hybridizing 3 p orbitals will just give you p orbitals. There's no mixing, there's no hybridization at all. So creating a hybrid orbital requires you to combine 2 or more different orbitals together. Alright, so by hybridizing this, we make an sp2 hybridized orbital, 3 of them, and 1 p orbital will be left unhybridized. Carbon has 4 electrons, so 1, 2, 3, and 4. Let's see if this hybridization matches up with our Lewis diagram. Alright, so 2 of these hybrid orbitals belong here and here. This 3rd hybrid orbital will be used as a sigma bond inside the double, while this unhybridized p orbital is going to be the pi bond inside the double bond. Alright, so everything matches up. Thus, this carbon is sp2 hybridized. Now, as I mentioned earlier at the beginning of this unit, a lot of the rules that we make up in chemistry are just that. They're just rules that humans made up to try to understand the nature of the universe. In the end, though, nature doesn't have to follow our rules. And in this case, nature will not follow our rules in most cases. So when we talk about the octet rule, we're saying that generally 8 valence electrons will provide stability. However, there are examples where less than 8 can provide stability and more than 8 can provide stability as well. Let's take a look at boron trifluoride. Fluorine has 7 valence electrons times 3 fluorines, so that's 21. Boron has 3 electrons for a combined total of 24 electrons. Boron has the greatest bonding capacity, so I'm going to stick in the center with fluorine sprinkled around it. Again, I know there's going to be at least a single bond between each of these. And of course, the fluorines must get priority when it comes to the octet structure. So I have drawn 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons. Now, the boron, of course, does not have an octet structure. The fluorines do. So this usually indicates that we're going to have a multiple bond present. So I'm going to take these 2 and bring them down here. And now we formed a double bond. So let's take a look at this. Fluorine has 8 electrons, so do these ones. Boron now has 2, 4, 6, and 8 electrons. Everyone has fulfilled the octet rule. But as we saw in the previous example, since I didn't have to choose this fluorine, I could have chosen this fluorine or this fluorine to donate its electrons. That usually indicates a resonance structure, with BF3 being a hybrid of these 3 resonance structures. Not a double bond, not a single bond, but instead a 1 1/3 bond in between. Or so we would expect. You see, through experimentation, we found that the data seems to indicate that boron trifluoride actually looks more like this. As you can see, boron only has 2, 4, 6 valence electrons around it, and yet it's stable. So this is one of those situations where nature is not going to follow our rule, specifically the octet rule. So we had to come up with an exception to the rule. We call this the incomplete octet or incomplete valence, where certain elements can be stable with less than 8 valence electrons. Now don't freak out, I don't expect you to know every single exception to the octet rule. This is an introductory course. So for now, I only need you to focus on group 2 and group 3 elements, specifically boron and beryllium. They are the ones you are most likely to encounter with an incomplete valence or an incomplete octet structure. Boron can form 3 bonds, 2, 4, 6, so it can be stable with just 6 valence electrons, while beryllium typically forms 2 bonds, and it can be stable with 4 valence electrons. So if you can have elements that can be stable with less than 8 valence electrons, you can also have elements that can be stable with more than 8 valence electrons. Let's take a look at PF5 for instance. So phosphorus pentafluoride, 7 electrons for each fluorine times 5 of them, equals 35 electrons, and phosphorus can have 5 valence electrons, so in total we got 40 electrons we had to work with. Phosphorus has the greatest bonding capacity, so I'm going to put that in the center with fluorine around it. We know that these ones have to be at least single bonds, and right off the bat we know that we've got an issue because we see 2, 4, 6, 8, 10 electrons around the phosphorus, and there might even be double bonds or triple bonds, so more than 8 electrons for sure. So phosphorus pentafluoride does not follow our octet rule, but it exists, so there's got to be a way to explain it. But before we do so, let's just make sure we can count out the 40 electrons to see that they're evenly distributed. Alright, so we've got 2, 4, 6, 8, 10 electrons. Make sure the fluorines get priority. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40 electrons, perfectly matching up with this. It doesn't have any lone pairs, so it has an AX formula of AX5. So that's going to be a trigonal bipyramidal. So I'm going to make it look like this, with 3 of the fluorines on the same plane, but 1 fluorine popping out of the page, 1 fluorine popping into the page. Trigonal bipyramidal because there's 2 pyramids, 1 at the top, 1 at the bottom. Trigonal because it makes a triangular shape, or triangular base for that pyramid anyway. Alright, so these fluorines are going to be on the same plane. 1 is going to pop out of the page, and 1 is going to go into the page itself. And there is our trigonal bipyramidal, with a 120 degree angle between each of these fluorines on that plane, and then we have a 90 degree angle here and here between the fluorines. Alright, so what I'd like you to do at this point is write down the Lewis diagram, AX formula, VSEPR geometry, 3D drawing, and the hybridization around the central atom for each of these 2. When you're ready, press pause, and then press play once you're done, and we'll take it up. Alright, so fluorine has 7 electrons. Since there's 6 of them, that means 42. Sulfur has 6 electrons, so altogether we have 40 electrons. Sulfur has the most number of bonding sites, so I'm going to make that my central atom. Fluorine will be all around it. I know there's at least a single bond between each of them. And then, of course, the octet rule must be given to those fluorines. Now, after that, 8 electrons for each. 6 times 8, 48. That accounts for all my electrons, so there are no lone pair electrons. As such, the AX formula is AX6, making it an octahedral VSEPR geometry. So we'll have 2 of the fluorines on the same plane. 2 will pop out of the page, and 2 will go into the page itself, giving us this structure over here. Now if I look around the sulfur, I see 1, 2, 3, 4, 5, 6 regions of electron density, so we need to have 6 hybrid orbitals. And so I'm going to need to hybridize 6 orbitals altogether, giving me sp3d2 hybridization. Sulfur has 6 valence electrons, so 1, 2, 3, 4, 5, and 6, which allows me to bond with the fluorines here, 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 and here. Alright, so we needed this expanded octet structure. Since sulfur is in the 3rd energy level, it is able to have a empty 3d orbital with which to hybridize. And the sp3d2 hybridization does a pretty good job of matching up with the Lewis diagram. With XeF4, I've got 7 electrons for each fluorine, 4 of them, so 28 electrons for the fluorines. Xenon has 8 valence electrons for a total of 36 electrons. Xenon has the greatest bonding capacity, so what I'm going to do now is 1, 2, 3, 4 of the single bonds. Each one is a 2, 4, 6, 8. Then give priority to fluorines. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. But I'm supposed to have 36 electrons, so that means 34 and 36. So I'm going to have some lone pairs there. As such, the AX formula for this will be A for the central atom of xenon, X4 because there are 4 fluorines, and E2 because of the 2 lone pairs. AX4E2 has a square planar geometry where 2 of the fluorines will pop out of the page, 2 will pop into the page, and the lone pair electrons will be on the plane of the page. And thus would be our 3D structure. So square planar because it makes a square shape all in one plane. Looking at the number of electron densities around the xenon, we see 1, 2, 3, 4, 5, 6. So I'm going to need 6 hybrid orbitals, requiring me to hybridize 6 orbits. So once again, we'll have sp3d2 hybridization in order to provide me with 6 hybrid orbitals. Xenon has 8 valence electrons, so 1, 2, 3, 4, 5, 6, and repeat 7 and an 8. We'll see that these are the 2 lone pairs, leaving me with 4 empty spots for each of the fluorines. Whoops, I seem to have deleted the fluorines here. So fluorine, 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 and fluorine. So again, hybridization does a pretty good job of explaining, or matching up anyway, with the expanded octet structure. Again, xenon is past period 3, so it does have empty d orbitals with which to fill in and hybridize. So going back to this worksheet, you should be able to do SEF6 now. If you look at the answers on the back, it is a octahedral AX6 shape. I don't think you need me to go over this one, but SO2, now that's a special case. Let's try this one out together. So with SO2, oxygen has 6 electrons, there's 2 of them, giving us 12 electrons. Sulfur has 6 electrons, giving us a total of 18 electrons. Now both sulfur and oxygen have the same number of bonding sites, and that is 2 areas where they can attach onto other electrons. In such cases, the central atom is typically the least electronegative. So over here, oxygen has an electronegativity value of 3.5, while sulfur is a 2.5. So sulfur should be the central atom. It just doesn't look right when it's unbalanced and not symmetrical this way. Nature loves symmetry, and this molecule is definitely not symmetrical. Alright, so let's put a single bond between them. And of course, give priority to the oxygens, make sure they fulfill the octet rule. So 2, 4, 6, 8, 10, 12, 14, 16, and I need to have 2 more, so I'm going to put one over here. This gives us 18 electrons in total. However, although the oxygens fulfill the octet rule, sulfur does not. As I said before, it's usually group 2 and group 3 elements that are going to exhibit incomplete octet structures. Sulfur, on the other hand, does not fall in the group 2 or group 3 category. So that indicates to me the presence of a multiple bond. So I'm going to take these 2 electrons and bring them over here, creating a double bond. Now this oxygen has 8 electrons, so does this one, and so does the sulfur. Now since I didn't have to choose this oxygen to donate it, I could have chosen this oxygen here. That usually indicates the presence of resonance. So the other resonance structure will look like this with a double bond on this side. But of course there is no real double bond, no real single bond. Instead the electron has been delocalized, and so it's going to be something in between a single bond and a double bond. In this case, 3 bonds divided amongst 2 areas. So it's going to be a 3/2 bond, or a 1.5 bond. Now looking at this, it has an AX formula of A, X2, and an E. Alright, so the 2 oxygens are the X, and then 1 lone pair sitting at the top, so AX2E, and that would be a bent or angular VSEPR geometry, giving you these 2 resonance structures if you were drawing them in 3D. Now the reason why this question is so odd is because if you try to look up the Lewis diagram on Google Images, you'll find this potential diagram as well. So in both cases, it's still a bent VSEPR geometry, but in one you have resonance and the other one does not. So the reason why this structure is valid is due to something called formal charges. Now don't worry about formal charges, it's not in the curriculum anymore, but you will see it in first year university, so I might as well just introduce it to you anyway. Let me just put in the lone pair of electrons around the oxygens first, because that will make things easier to see. Okay, there we go, and here, and this one gets this one gets this, and this. All right. So let's see how this works. With something like lithium, for instance. Lithium has two options to achieve stability. It can either lose one electron, and once it does so, this whole valence shell disappears, and now it has a full valence shell. Now it's isoelectronic to helium, and it's stable. The other option, however, is to gain 7 other valence electrons, and that would allow it to be isoelectronic with neon. But what's easier to do? Which direction do you think nature is most likely going to take? Lose 1 electron or gain 7 electrons? Obviously, gaining 7 is more work than losing 1. So lithium is more likely to lose 1 electron to achieve stability than to gain 7. Well, let's zoom in on this example here for a second. So all I've done over here is just color-coded whose electrons belong to whom. Remember that a single line represents 2 electrons because it's 1 chemical bond, and 1 of the electrons belongs to the oxygen, 1 of the electrons belongs to the sulfur. So here's that little single bond. 1 of the electrons belongs to the oxygen, 1 belongs to sulfur. Because it's a double bond, well, then I've got 2 blues and 2 reds. Over here we have a single bond, so 1 blue, 1 red. Now sulfur normally has 6 valence electrons. But take a look at this. This sulfur has 1, 2, 3, 4, 5 electrons that belong to it. So if we look at how much it should have versus how many it currently has, we see that this sulfur is currently missing 1 electron. This number that we calculated here is known as the formal charge. Basically just take how many electrons that element is supposed to have, subtract how many it currently has, and then that is the formal charge value. So this sulfur over here has a formal charge value of +1. Looking at this oxygen, normally oxygen has 6 electrons, so 6 electrons, and right now it has 2, 4, 6 electrons, and so its formal charge value is a 0. So I'm going to write down a 0 for this one. For this oxygen, once again, normally it's supposed to have 6 electrons, but over here currently has 2, 4, 6, 7 electrons. And so its formal charge is equal to -1. So I'm going to write down -1 over here. Now let's look at this diagram over here. So sulfur, sulfur, it owns these 2 electrons. Since these are double bonds, half of them are contributed by the sulfur, the other half are contributed by the oxygen. So therefore 2 electrons belong to the sulfur. Same thing over here. Half of the electrons in these 2 bonds belong to the sulfur, while the other half belong to the oxygen. So 2 belong to the sulfur, 2 belong to the oxygen. Let's now calculate their formal charges. With oxygen, it should have 6 electrons, and it currently has 1, 2, 3, 4, 5, 6. So 6 minus 6 electrons means 0, so its formal charge is going to be a 0. For sulfur, normally it also has a valence charge of 6 electrons, and currently has 1, 2, 3, 4, 5, 6 electrons, so 6 electrons minus 6 equals 0. So it too has a formal charge of 0. This last oxygen, same calculation, will also have a formal charge of 0. Now this is not a perfect explanation, but one way to look at formal charges is to think of it in this manner. In order for this molecule to achieve stability, this sulfur had to be missing 1 extra electron. It should have 6, but instead it only has 5, so it's missing 1 electron. Whereas this oxygen over here should have 6 electrons, but instead it has 7, so it's got an extra electron, resulting in a formal charge of +1 and a formal charge of -1. This oxygen is fine. It's supposed to start off with 6 and it ends up with 6, so very little changed with this one. Looking at this structure over here, oxygen should have 6 electrons, and it does have 6 electrons. Sulfur should have 6, it also has 6, and so does this oxygen over here. So in order to achieve stability, the electrons didn't really have to move too much. There didn't have to be too much change in electron numbers. Well, just like how it's easier for lithium to just lose 1 electron rather than gaining 7, the fewer you have to change, the fewer electrons that have to move around, the more likely for that structure to exist. So since this Lewis diagram of SO2 seems to require the fewest changes in the number of original valence electrons versus how many it currently has, it is more likely to exist than this one, which required more electron movements than this one. All right, so again, formal charges is not in our curriculum, but it's something that it's nice to know going into university or college. All right, so although these drawings are all valid, this one, according to the formal charge theory, is more likely to exist because it has the fewest requirements in terms of electron movement than on this side over here. Now, because it's not in the curriculum, either of these answers is acceptable to me. I mean, take a look at this. 2, 4, 6, 8, octet rule. 2, 4, 6, 8, octet rule. 2, 4, 6, 8, 10, so expanded octet rule, which is allowed because sulfur is in the third shell, so it does have an empty 3D orbital to expand into. So this drawing is also valid. Either drawing is valid on the test and would receive full marks. Alright, so in our next video tutorial, we'll figure out how to fill in this column, how to determine whether a molecule has a dipole present or not.